Start now, right? Okay, good afternoon, everybody. Welcome. So we have a very special colloquium guest today. It's my great pleasure to introduce our newest professor in condensed matter physics, Professor Valetin Crepel, who recently joined us as an assistant professor just this semester officially or over the summer. So Valentin has been sort of split, I think, between Europe and North America for most of your career so far, beginning in France and doing your bachelor's at MIT, then a master's back in France again, and then a PhD back at MIT, again with Liang Fu. And then I suppose your wave function sort of collapsed and you've been staying in North America since then. Had a postdoctoral fellowship at the Flatiron Institute before joining us recently as assistant professor here at the University of Toronto. So Valentin is a theorist who studies strongly correlated quantum matter with a particular focus on moire materials and two-dimensional materials, where geometry and subtle effects of symmetry affect electronic structure, in particular twisting, lattice registry between different materials, govern interactions between electrons. Among his notable contributions are an exact theory for superconductivity emerging from strong repulsion, which offers a clean mechanism relevant to unconventional superconductors and moire platforms, which is something that's near to me and to my students as well. And I would say insights into topological flat bands. Hopefully we'll hear something about that today. And flat band systems, including twisted bilayer graphene. So I would say his work generally has clarified how these topological bands arise and what kinds of correlated physics can be hosted in those systems. He was recently recognized for his work. In fact, I think just last month, it was announced that he was the recipient of the 2025 Blavatnik Regional Award for Young Scientists in Physical Sciences and Engineering. So congratulations on that award. And as many of you know, my group is interested in these systems and studies them experimentally. And I can say from firsthand experience that Valentin's work is really invaluable in this field. The parameter space for these structures is just enormous when you combine all the different kinds of materials and structural parameters, twist angles, and arrangement of the layers. It's really vast. And I think searching through this parameter space exhaustively is essentially not possible. So insights from his theoretical work that give us some guidance and some direction in this area is really much appreciated. So I think that not only we, but the broader community is going to benefit from his work, some of which you'll hear about today. So please join me in welcoming Professor Valetin Crepel.
Thank you, Sergio. I hope the talk lives up to the praises. Yeah, and I think you've heard a 2-minute summary. That's better said than what I can achieve. So keep that in mind if you miss the point of the talk in the end. I thought the colloquium was also a good way to present myself and present the research I do in a broader context. So we'll talk about quantum simulators, but just to begin with, let me put myself in the space of quantum matter theories and what my research focuses on. So I study the quantum many-body problem, which is just the study of many quantum particle in interaction. And there's a big issue with that, which is very simple to phrase, which is if you have n, let's say spin 1/2 interacting, your wave function, because it is a superposition of all possible single particle states, so of spin up and down, is exponentially large. So you have 2n possibilities for putting a n spin 1/2 into two configuration. And because of this exponential growth of the Hilbert space, it's very difficult to tackle these systems. And if you just want to store one complex coefficient for each of these configurations and have 75 spin 1/2, well, you would need 200 zettabyte of storage. And that is just to store the coefficient, not even do anything with it, like know if that is a good wave function or not. This is more than what we have currently in the entire world. And so, yeah, this is just not possible. And again, 75 electron is what belongs to an atom. So if you think about doing materials afterwards, gets very complicated. Fortunately for us, most problems that we study actually don't need those 2 to the n possibility, and most problems just need a subset of this coefficient. So the simpler one, let's say what I would call classical problems. So if you have an unfrustrated quantum ferromagnet, its solution basically look like a classical ferromagnet with all spin pointing into one direction. So you get only one state here. So that's very easy. Then you need one coefficient and not 2 to the power of n. So that's one set of problems that are easy. A second set of problems that are easy to look at are those that I would call low rank, where basically by going into a real rotating frame for each of the spin, you can still describe the system with what we like a classical solution that only retain one or a few of these coefficients. And then the optimization is just finding the good basis in which to express your system. So if you're smart enough, you can describe all of this system. Or there's also a numerical algorithm that we can build that extend the boundary of this low rank approximation and can tackle a lot of these single part, many body states at the same time. Yeah. And then there's all of the hard problems that don't fall into this category, that are low rank wave function, and where you can prove you need a lot of this coefficient, a large fraction of them, if you want to faithfully describe the system. And unfortunately, all the problems that I like studying are in this region of hard problem. And these two examples are high TC superconductors or fractionalized topological phases. And broadly speaking, if you put two axes into that potato chart, if you add topology and add interaction, at some point you will reach this hard barrier, which is where I try to make an impact. So let me just drive you through these two examples because they will be relevant to the second part of the talk, but also because, again, it kind of introduces to everybody what kind of research I do. And these are the problems I spend most of my time looking at, as Sergio said. So the question of high temperature superconductor is what really differs between superconductors that we've observed that are called cuprate or other high temperature superconductors that start superconducting at temperature that are of the order 100 Kelvin. So what's the difference between those and the conventional superconductors that was discovered before and have low transition temperature, critical temperatures? And in essence, superconductivity always happens in the same way. So electrons are fermions, and they need to bind to create bosons. And these bosons condense into superfluid, and that superfluid can propagate electricity without dissipation. So the mechanism is the same. The difference between those two materials is kind of in the details, where if you look at the conventional material, the typical pairs that you form are large compared to the lattice constant. Another way to say this small, to put this small large scaling is to say that the attraction and repulsion of the fermions when they bind is small compared to the kinetic energy. And because you have this separation of scale, you can have a like general theory that encompasses all of this material, and then all of them are very well understood. We have good idea of if you get this material, what will be the critical temperature. On the other hand, high temperature superconductors, their particularity is that the pairs form, the pair size is of the order of the lattice constant. And this is where the atoms almost repel the most because of the Coulomb repulsion. So this is where you really need to understand how repulsion can drive attraction in this system. And you need to combine them at the fundamental, you need to have one theory for that includes interaction. And so you're part of the hard problems, as I phrased it in my potato chart before. So that's one class of hard problem. The second class of hard problem that I want to introduce, and again, will be relevant later, are topological phases and fractionalized phases. So those ones are less intuitive than pairs being large or small, but I can draw an analogy with things that you probably know. So when we speak about topology, we think of the study of surfaces. And the most known example is how many holes in the surface is there. And that is given by a number that is called the genus. And so the coffee cup has a genus of 1, and you cannot adiabatically deform it into a sphere because you have to puncture to remove the hole at some point, which is not an adiabatic process. And so if you're just a point living on a surface, locally, you wouldn't know the difference between whether you're living on a sphere, a coffee cup, or glasses. All you can see is just 2D space. But if you're allowed to run through the entire space, then you will start to notice that your surface may have holes. And if you count that number of holes, then you can tell what's the topological invariant. So in a sense, topology just means that you have some systems that are not differentiable by how they look locally, but only if you explore their property globally, then you realize that they are different. Right? And this difference is usually classified in terms of topological invariants that are integers. So here the genus. So now if you're an electron in quantum mechanics, you're just some wave function, so some vector in the abstract space. But you also live on a surface, which is momentum space, if you evolve across the plane, let's say in 2 dimensions. And so your motion across the 2D space may have some nodes as well if you explore the entire system, but locally you would just feel like you're living in 2D space. So electrons also can be in phases where all of the local properties of these phases are similar, but the global property of the wave function as you move through the entire space is different, just like a point moving on a surface would see holes there. So they are slightly more involved mathematically, but it's the same notion. And again, these different phases are then classified by topological invariant, which are integer. The most famous of them is the Chan number. And the Chan number gives you insight about the global properties of the system. In that case, how many dissipationless edge modes there is on the edge. And to probe the edge, you really need to probe the global structure of the wave of the system. All right, something extremely weird happened when you add interaction to that picture is that people have realized and measured experimentally that in presence of interaction, those topological invariants can take fractional values, and this should not be allowed by mathematics. So it's as if you were breaking the Gauss-Bonnet theorem in mathematics. Usually breaking a theorem is not good. And what happens here is that, in fact, the electron in presence of interaction splits into 3 new types of particles. So electrons are no longer the elemental constituent of your system, but you have new things that look like anyons that are called anyons, have fractional charge and fractional statistics that constitute the edge mode. And this is, again, something that belongs to the hard class of problem because you need interaction to go from this integer classification to the fractional classification. Right, so this is an overview of basically who I am. And you will hear basically 2 talks from me if you stay long enough in the department. One is how to extend the dark blue region here by using better algorithm. So to push the limit between low rank and hard problem with algorithm like tensor networks. And the second one is a flavor of what I will give today is use quantum simulation to tackle this hard problem. So it's basically use an analog quantum system to solve this hard problem, just trying to give some design principle to experimentalists so that they can answer the question for me. So the idea of quantum simulation comes back from Feynman, who basically said that we have a difficult problem that we cannot simulate classically because of this fundamental problem of many-body interaction and superposition principle. So let's just find an analog quantum system over which we have more control so we can draw more information out of it. Otherwise, it's just useless to have an analog quantum system. And let's tune that quantum analog system in a state that looks pretty similar to our physical target. And then maybe we get enough information out of this system to learn something about our original problem. So this flowchart is a bit misleading because what happens in practice is that all of these arrows are kind of inverted. So what you want to start from is a good quantum system over which you have a lot of control, because at the end of the day, if you don't have enough control and don't have enough measurability of ease of measurement out of this system, you won't get enough property, and that will basically, you will be back to step one of finding a good quantum simulator for your quantum simulator. Right? So you want controllability and ease of measurement out of your analog quantum system, and then enough tunability so that you can put the system in a state that looks like one of your physical targets. So these are what I would call experimental requirements: controllability, tunability. And then there's what I do, which are the theoretical requirements. Is when I'm handed a system with enough tunability, how should you play with your system to design a phase that is of interest? So one phase that is in this hard class of problem that we don't know how to tackle classically. And this is what I will talk about. So what I want to convey today is that van der Waals heterostructure are good quantum simulators because we now have enough control over them to really create new Hamiltonians. And then I will show you how my research has been applied to this material to basically design new phases, to guess how to design new phases of interesting system in this system. All right, so I hope this is clear. So without further ado, let's go to the materials that I will be interested in. So what are van der Waals heterostructures? These are simply stacks of two-dimensional materials that are formed by just putting them on top of one another mechanically. So this is a field that started with the exfoliation of monolayer graphene around the year 2000. And since then, many more materials have been exfoliated. So you can really build stack out of graphene, but many other materials. Difference with 3D bulk materials that you have somehow in your phone or elsewhere is that there's no chemical bonds between the layers. And the layers are held together by weaker forces that are called van der Waals forces. So hence the name of van der Waals heterostructure. And what this basically achieve for you is a lot of new degrees of freedom. If you want to stack two materials that are chemically bonded, then you cannot take two materials that are too far different. Otherwise, you will induce strain at the interface, or defect, dislocation, and physics that is not pure in a sense of growing a material. So you basically end up stacking gallium arsenide with aluminum arsenide, which, because they are close in material constituent, chemical composition, they also exhibit similar properties. Right? What relieving that constraint of chemical bonding between layers give you is that you can pick any material and put it on top of any other one. So you can take a semiconductor and put it on top of a supraconductor, or you can take a magnetic material and put it on top of a metal, or really you can do anything that you want. And by anything that you want, what I really mean is for each of the layers in your stack, you have about 2,000 possibilities of materials that we know would be stable in 2D form. So this is, and they are compiled in online databases. You can look them up. So this is 2,000 materials that are known theoretically to be stable. I think about 100 of them have been synthesized to the monolayer limit experimentally. And just one example of what you can do by just stacking things together is you can take graphene and so graphene was always envisioned as the new generation of transistor, but the difficulty was to induce a gap so that you could actually perform, you would have an on and off switch for letting information pass through or just stop it with a small gap. But inducing that gap in graphene has been quite difficult. But this is something that you can do by just adding below graphene a monolayer that has a strong spin-orbit coupling that can induce on the bilayer graphene some spin-orbit coupling and open the gap of graphene, as you can see in the splitting here. And so that's just one typical example of what you can do if you are not bound to have any chemical bonds between the two layers. So these materials are extremely versatile, not only for their chemical composition, but also because of their tunability. And the tunability, what condensed matter physicists have resorted to change the physical property of semiconductors the one way they've designed new system with property that go beyond the properties of their constituent was to do superlattices. So one example is the stack of gallium arsenide, aluminum arsenide that I showed above. Just stack them and do 1D superlattices out of them. And this stack turns out to be a quantum cascade laser. So it has different optical properties than each of the monolayer that you've put in independently. So making some superlattices brings out new physics at the forefront. And very fortunately for us, 2D materials basically have also their version of superlattices a bit built in, because whenever you stack two materials that are a bit mismatched, either because they have a twist between because there's a twist between the two layers, or because there's just a lattice mismatch between the two materials that you're looking at, you will have this long wavelengths moiré pattern that will appear. So these are interference patterns made by the lattice of the bottom layer and the top layer. And this naturally arise. So that doesn't mean that it's useful for any purposes, but there was one groundbreaking experiment in 2018 in the field that shows that those interference patterns are actually good for something, and that they can promote new physics out of in your bilayer that did not exist in the monolayer. So that's probably what Pablo Herrero talked about at the Waals lecture last year. And what he did is, what his team did was take 2 layers of graphene, twist them by about 1 degree, and they saw emerge a superconductor, while none of the graphene sheet by itself is superconducting. So again, making a superlattice out of things give property to the system that did not exist in the monolayer. And so that is the tunability of moiré systems, right? Yeah, and the second thing I want to point out about this experiment is that you should be amazed that this phase diagram was taken with only one device called M2 here. So you have access to an entire range of density and temperature, but this is more common in condensed matter, out of only one material. Usually, if I compare that to high temperature superconductor, getting the phase diagram, it's much harder because you need to grow each sample, like bulk 3D sample, independently. Carefully dose the number of dopants you put in your system. Make sure that this does not induce any defect. And then out of each of these material carefully designed, you get one data point. And then you collapse all of these data points for different material classes and hope to get a comprehensive or something that makes sense as a phase diagram. And here you really get everything within one sample. And so what took you 20 samples here, take you 1. So you can make 20 devices of that and look, for instance, how the superconductivity depends on the strength of superconductivity depends on the twist angle. And so that gives you another node to understand more the physics, right? And how this was done is just because 2D system only take 2D amount of space, you can engineer the third dimension to make here a capacitance that changes the electrostatic potential at the level of the monolayer. So you basically charge carrier into the bilayer graphene by just changing the gate voltage in your capacitor. All right, and those systems, the last thing I want to point out is that those systems also have a lot of measure. So experimentalists have figured out new ways to measure the system. So not only, like I would say, standard global transport and optics that people have used in condensed matter, but other new kinds of sensing capabilities. So one of them that I really like is to put a sample layer and a sensor layer. So this is a material that you know, this is a material you don't know, and you infer the physics of the sample out of the physics of the sensor. Sorry, I mixed them up. But so by looking at the material that you know very well, you can infer what's happening in your sample layer. And this is, again, as you see, some environment engineering given access to you by the third dimension that you're not using, right? And the second thing that is very nice about 2D material is that if you do 2D spectroscopy, you get information about the entire system because the surface of a 2D system is the entire system. While non-penetrating microscopy, usually for bulk material, only probes defect that happen at the surface. So, okay, this is a bit maybe giving too much praises to this material, but I really want to convey that these are good material for quantum simulation because they are versatile, tunable, controllable, and it's easy to measure them. There's one caveat, which is maybe the scale of the moire. Because it's long compared to the lattice scale, you get small momenta, and small momenta mean small energy scale. So you need to cool down the system much further if you want to see the same phases in moire system compared to high temperature superconductors. But this is a good platform for quantum simulation because you only want to do the quantum simulation out of a fundamental science perspective. And then you do it once, you learn about the system, and you go back to your standard bulk material if you want to increase TC. The second thing is, Sergio mentioned it a tiny bit, it's the parameter, tuning parameter landscape is extremely vast. So we have twist angle, gate voltages, the type of material you put on top of one another. So this is extremely vast, and knowing how you take, what material you should put on top of which other material at what twist angle if you want to reach, this specific phase of interest has become extremely hard. And this is where my work comes about. So my work is basically trying to give hints on what to do to this system, which materials to take, how to twist them, what gate voltage to apply to realize specific phases of matter. I will just illustrate that with two examples. The first one is mimicking the physics of topological phases. And the knobs I will allow myself to play with is chemical composition of the bilayer or the architecture, so what kind of gate voltage I apply to the system. So in more details, I will consider homobilayers, twisted homobilayers of 2D semiconductors on the one hand, and on the other hand, I will consider this other type of moire material I did not touch upon in the introduction, which are electrostatic superlattices. Essentially, these are just a monolayer of 2D material that is put on top of a edged or patterned dielectric. And then if you apply a gate voltage at the bottom of that dielectric, the potential on the monolayer will not be uniform. So it will have some bumps, maxima, minima, and so that will change the physics of the system. So it's basically just inducing a long wavelength superlattice, just like a cold atom people apply laser to trap atom, essentially. But this is exactly the same way. Right. The physics of those materials can be understood in the following way. So you have a 2D monolayer. An electron in that monolayer have some dispersion relation. So for each momenta, they have some energy. And when you apply the superlattice potential or the moire pattern, this dispersion relation will be cropped. And each of these points will be connected to its image in momentum space due to the superlattice potential. So the way we reason about that is not show it into the extended momentum space, but we fold all of the band structure into only one of these unit momentum space cell of the superlattice, what we call the mini Brillouin zone, or Brillouin zone, but for the superlattice. And then each of the point at the edge of the mini Brillouin zone will be connected to the point at the other edge by the superlattice. So basically you have the superlattice connect this point to that point and will open some gaps, right? So the idea we had is, can we infer topological invariant by just including the simplest form of superlattice potential or interlayer coupling in the system? And the simplest form is just looking at first order perturbation theory. So we know the superlattice shape, we know its harmonic. So we basically know how the eigenfunction here and the gap scales with the original wave function of the material and the strength of the harmonic. And because you have access, and just doing that turned out to be very fruitful, because there are theorems that tell you that topological invariant can be extracted from just knowing the wave function at the points where the gap opens first, if you have sufficient symmetries in the system. Okay, so this is all the work by, for instance, Liang Fu or Andrei Benlevik around the year 2010. What that look like for two-dimensional material is something like that. So if you plot the velocity field of electrons in momentum space, you don't really need to know what this is, but you see that all of the action happens at very specific points, and in blue and red here. And these blue and red points are the points that are where the gap first open perturbatively. And so if you have a system where you have both blue and red, they basically cancel out and give you a Chern number 0. And you have two blue, they add up, giving you a Chern number 1. So this is how you can read topology from high symmetry points. So it's very sketchy. There's actually formal math behind it, which just gives you a flavor of what we actually do in the calculation. We include the field, so we get the wave function at each of these hotspots. And then we look at the symmetry property of this hotspot and basically infer if they are red or blue. If they cancel out, Chern number 0. If they don't cancel out, then we have topological property. And then we can do that systematically, including, let's say, for the superlattice material, any material and any superlattice potential that you apply. And the only ingredient we have in the theory is what kind of superlattice you've applied. So the symmetry of the superlattice that you applied, whether it's rectangular, then the symmetrical group is C2, so rotation by 180 degrees. Here it's triangular, so it's a honeycomb. So it's a C3 rotation symmetry. And then you can have a square or a triangular lattice as well. And just given the geometry of the superlattice that you apply and a few material coefficients, typically 5, I can give you with some formula that combines everything I said so far, the Chern number. And in this plot, there are many colors. All you have to care about is that if it's red, it's topologically trivial. If it's not red, then it's interesting because it realizes a topological phase. And that tells you something about the system. If you give me a monolayer material, I can compute those coefficients and tell you which superlattice you have to apply to get some topologically non-trivial phase. Or the other around, if you really know that this is what you want to work with, I can give you materials that will realize some specific topological phase. You can do the same game for the twisted semiconductors that I've described before as well. So because there are just too many of them, like 2,000 in total, I will only show here the semiconductor that have C3 symmetries from the database, and I can really list them all, perform that small perturbation theory, and tell you which of them, which are shown in red here, will be topological if you do twisted structure out of them, which of them will not. And I can also give you like a hint of at which temperature you will see that topology through the gap that opens. So the size of the gap will tell you at which temperature you may observe those states. So a very good one here you see for topology would be MOTE2, which is a transition metadical cogenide. And this has been seen experimentally. This is one of the leading platform where people see topological phases so far. Right, so this is engineering topological phases of matter, which is kind of how do you design the single particle physics in the system? Now I want to turn to how can you engineer two-body interaction in the system? And for that, I'll go back to my high temperature superconductor example. And the goal here, I remind you, is can I design this hetero bilayer in a way that they have short range attractive interaction that allow for the formation of pair, and the size of this pair be of the order of the lattice constant. And so that will help me understand something about high TC superconductor, how they can emerge, and how the physics can play out. Right. And just to speak about attraction versus repulsion, I need a reminder of scattering theory. So how do we define attraction versus repulsion in a quantum system? Basically, you just send a particle against another, and you looked at what comes back. And because particles are wave in quantum theory, if the wave that comes back is in phase with the wave that you sent, there was no interaction. It was perfect reflection. If now the two particles attract, the two particles will spend some time together before leaving. And so the reflective wave will be retarded compared to what you send. The other way around, if they repel, what you send comes back faster because they don't want to be next to one another. And so by just looking at the phase shift or the reflective wave and how much time they spend together, you can infer something about the attraction versus repulsion in the system. And the first people who really understood that deeply, I think, are atomic physics people who used that precisely to tune the interaction between two neutral atoms from repulsive to attractive. And the way they've done that is take a molecular bond state, which is a closed state, and put it close enough in energy to the scattering energy of two particles. So if two particles collide and have a molecular bond state that they can hybridize with, then they will virtually occupy that bond state, spend some time together before decay back because that molecular bond state is not the ground state, and then come back to you. That is a positive phase shift. So the phase of the reflected wave is retarded, and that induces some attraction. If that attraction is greater than the original repulsion of your two atoms, then you're good. You can induce superconductivity. And they've actually been able to not only induce superconductivity and form these long scale pairs, but they've able to go all the way down to the BEC regime, where the pairs are extremely small. So cold atoms don't have a lattice, so they can go basically as small as molecule can go. But in condensed matter, we would just hit some barrier here that is the lattice constant. And we just basically want to mimic their idea because they were smart before us. So the only question is, can we have a version of the phase path resonance that we can apply to condensed matter system? So what are the fundamental thing, like ingredient that we need? So we need electrons that we do have. The harder thing is to have that molecular bond state. Just by charge conservation, if we want two particles to hybridize with this molecular bond state, it needs to carry charge 2e. And those charge 2e objects are just harder to find in condensed matter system because they are charged. And they need also to be like kind of local. So the first question was, is that even possible? And one thing that we realized is figure out a minimal model where they do exist and they can drive superconductivity, which is what Sergio hinted at during his introduction. So the model is kind of simple, and you can think of it as having two layers on top of one another, where the sites where one of the layer lives at the Moiré scale is offset compared to the other layer. So each of the blue sides here correspond to one layer, and it's shifted down one in energy. So every side of that layer is filled. And the red dots here belong to the second layer. And the only thing we keep in that model is the dominant intra-layer interaction, so on-site interaction, and inter-layer interaction, nearest neighbor interaction. All right. And because all of the blue sites are occupied, you can look at all of the excitation of the system. The simplest one is moving one blue dot to the red lattice. That is an exciton, so one hole, one electron somewhere. And that is just, what's called an exciton. And then you can bind that exciton to one additional charge. This is called a trion. But you can also bind it to two charges for this specific lattice that we've chosen carefully. The name depends on the literature, but let's call it a quadron. And the nice thing about our model is that this quadron is lower in energy than any other of these excited states. So then when two electrons are close to one another, they hybridize with this molecular state, and they decrease their energy by a larger amount than if they were far apart and only hybridizing with this one. And so you can replay the phase path resonance and say it's better for molecule energetically, for two electrons energetically, to be close to one another because they will reduce their energy through this hybridization here. And they can only do so to a lesser extent if they are far apart. Right. So we did some numeric to check that indeed everything works. And indeed, we get superconductivity in this system. This is not really what I wanted to point out now. What I really wanted to point out is we can also plot the pair wave function at the top of that dome of the critical temperature. And what we observe, so this plot is basically, if I have the first particle of my pair at the center here, how much probability do I have to see it at the other side on the lattice, to find the other particle of the pair everywhere on the lattice? And so you see that it's, the pair is almost only living on the nearest neighbor sites. So it's a very short range pair that basically look like high temperature superconductor pairs. So it's very local in real space. So again, we can quantify that. And for the people who want to know, in this system, we can reach a critical temperature of a Fermi temperature of about 0.1, which is the limiting range of the what high temperature superconductor achieve as well. Okay, so this is a bit of a sketch. It's an idealized model of what can happen. Doesn't mean it does happen or it will happen. I'm very confident it will in the next few years because of these two pieces of experiment. So the first one has proved that Feshbach resonance do exist in the solid state between these excitonic-like excited states. So that's an experiment from in the group of Atak Imamoglu in Zurich. And what they've probed here is a Feshbach resonance driven by an electric field, not between a charged Dewey object and, as I was saying before, but between an exciton, which is neutral, and an electron. So it's not the same thing. It doesn't induce superconductivity, but it's one form of Feshbach resonance that you can also drive between two different objects. So that's one piece of experimental data. The second piece is that the charged Dewey object that I was discussing have been measured experimentally. So they are not exactly the one that I showed you before, but they look almost similar. You see one hole here and 3 electrons. And they were seen spectroscopically as the Q line here. And if you remember the beginning of the talk, all we need for superconductivity is this Q line to be below the T trion and exciton X naught here line. So we are getting there, but still haven't found quite the right sweet spot in terms of engineering the bilayer correctly to find this quadrant way lower in energy. Okay, so that brings me to what I think we can hopefully achieve in terms of superconductivity. And I just want to open the discussion to what can we do when we have both things. So we know how to induce topology. So I've only showed single particle topology with integer chain number, but we've had also success in the community at finding phases that have fractional topological invariant, as I was showing before. So where the electron is fractionalized into anyons. The groundbreaking experiment is from 2023 in that Nature paper. We know how to induce superconductivity. And now if you just combine them in the left part of your system and right part of the system, respectively, so you have a superconductor on that part and a fractional chain insulator or fractionalized phase of matter on that left part of the system, then you can think about trapping an anion at the interface between the two. And I'm, again, confident the field is moving in that direction because the groundwork for inducing non-homogeneous gating that creates two phases that are different on two sides of a system are underway. So you see these are recent experiments where here you stabilize two different fractionalized topological phases on the two sides of your domain here. And this is another piece of work where they induce superconductivity next to a topologically fractionalized phase. So you could think really about this kind of structure. And now that you can move anions, you can think about doing more things. One of the things that is often cited is universal topological quantum computing with those anions. Yeah, so I hope I've convinced you that the 2D heterostructure von der Waals materials are good quantum simulators, and we also have enough theory to understand them and drive the experimentalists in the good direction to help them understand what combination of all parameters in the large parameter space they have to deal with will lead to topologically interesting phases or superconducting phases. And this is all I had today.
Okay, thank you very much. So we open up the floor for questions.
Yeah, thanks for the great talk. I was wondering, you mentioned earlier that these heterostructures are susceptible to disorder. Is that like a concern if you want to actually make a simulator that, say, Anderson localization is going to mess with what you're actually doing, or is that not is that something you can kind of mitigate?
Yeah, so disorder is, okay, obviously if there's too much disorder, it's always bad. But you can think this is why we kind of like topological phases, is that they are robust to what happens in the bulk. So if you have a bit of disorder in the bulk, it doesn't really matter because all of the action happens on the edge. So this is why this is the primary focus of my work. Yeah, so that's one. Obviously, like disorder is bad if it's too big. For all of the phases that I've described, disorder is usually not too bad because they are insulating for charge 1e excitation. So everything that carries charge or can be trapped in the effect doesn't really matter for those phases. For superconductivity, it depends on the superconducting state that you have and the scale of the disorder. So if it's S-wave superconductor, we know that disorder is not too bad for those kind of superconductors. Yeah.
Okay. Yeah. Thank you.
Other questions? How about twist disorder, by the way? Moire disorder.
Oh yeah, this is much harder to predict. So the twist disorder is because so I've shown a very simple picture for twisted heterostructure. What usually happens is that the atoms prefer one of these special stacking configuration and will just form disorder in twisting to have bigger size of that stacking configuration in that bilayer. And that can change the physics, but that happens typically at lower angle. So if you are at 5 degrees, the twist order disorder is not that much because the elastic energy that you have to pay to deform the lattices and create this twist disorder is just too high. At low angle, the kinetic energy of the electrons is small and smaller compared to the elastic deformation. So the system prefers to do elastic deformation to lower its energy to begin with. So yeah, at 5 degree angle, then you're safe, and then lower, it's very hard to model theoretically.
Other questions? I'll just use the chance to ask Valentin questions if you don't. So yeah.
What about the fractional translator superconducting junction is interesting, or could you provide more detail on that?
Right. There's compatibility relations. So you can think of, well, I should have oh, okay, it's here. Right. So this is why in our paper, we resorted to this weird fractional chain insulator, which is as anyons E/3, the one that I showed at the very beginning, combined with its time reversal partner. There are some compatibility relation. So this phase breaks time reversal symmetry, just as if you were in a magnetic field. Sorry if it's too technical. And S-wave superconductor don't like breaking time reversal symmetry because the pair are between Kramer's conjugate. So you cannot really put them next to one another and hope anything nice will happen, because you will have a transition region where you will have an intermediate phase between the two. So you need to find a topologically ordered phase with fractionalized excitation that has the same kind of symmetries as your superconductor. So you could think of this with a p-wave superconductor, that would work. A fractional chain insulator with a p-wave superconductor, that will be easy, like something will happen at the interface. So there's all of this compatibility relation that you can understand systematically, but I think no one has really took its pen and paper and wrote everything down. Like, what are the nice, interesting interfaces to look at, and which one are not?
Other questions from the audience? So what's the material combination that you would want in order to achieve your purely repulsive superconductivity? And would you need to suppress phonon pairing?
No, this is a very, okay, and then I'm talking to Sergio, then I will, so I see it's almost 4. I don't want to prevent anybody from taking a cookie, but so here in my model, I've only included nearest neighbor interaction between these two sides.